Alright, hell yeah. So we have dynamics, and we have this problem right here. It's a robotic arm. It's rotating. This arm is rotating with a constant speed. You know what I mean? So if it's hooked up to a motor, that's going to be constant. Now, what we're trying to find is like, hey, maybe this isn't constant. And so what we're going to do, the whole idea of this video is like, can we set this up? You know, so instead of 0.8 meters, that would be like, 30 inches or something. I just did 80 millimeters. You know what I mean? So we're a factor of, because 800 millimeters would be 0.8 meters. So I just put 0.1. That's kind of the factor here. And I made this 60 millimeters. So we're basically the same right there. On my graph paper, it was important to, well, I measured out, we have 0.8 meters, so just to make sure everything is the same, I measured out 80 millimeters to here, drew a vertical line. Now, this setup, they say, starts at an angle of 30 degrees. And so what we know about 30-degree angles is if this is the hypotenuse of 0.8, the sine component is half. It's just 0.4. So at 40 millimeters, sorry if I said this was 8 millimeters, 80 and 40. At 40, I drew a vertical line. So this is going to be my starting point. And I guess let's just kind of get to the setup, because it was pretty easy to measure just some thick paper. And I mean, all we're doing is just kind of still like, who cares? You know what I mean? It's kind of interesting. I would use that phrase, who cares, when going like the extra mile to do something like this. But the reason is, like, or why would I do something like this, is because I think it's going to help you get 100% right answers. If you set it up like this, it's like a check in that, and you don't even, so before this I was just like, well, we can kind of, hell yeah. So in all these problems, you don't want to lose the forest for the trees, or whatever the hell that saying is. You kind of want just an overall view of maybe what's going on. And so we're going to take a look at that. And so the first thing I did is just, hey, I rotated this back this way. So if I rotate this back, hey, this arm has to go like that way. So at some point, maybe this rotates to here, and this arm is just totally horizontal. And if we're saying this is the angle is measured just from imaginary vertical line. Well, hell, that angle would go up to 90. And if you just guesstimate what this angle is right here, I don't know, maybe it's like 45. That's a pretty good guess. And so if this thing was spinning this way, it would go to 90. It would go from 45 to 90. That would be an increase in angle. But we know that it says this is rotating in a clockwise direction. And so let's do, and I thought that was kind of the harder way to go. So we're going to rotate this down, and then this arm's going to be down here. Let's go like just a little bit more. Okay, I think we're following like what's happening. And then if we say, hey, this arm is like that, and we measure that angle, well, that angle is now real small. So now we know something about this. We know that this angle, and that's the question. It's just like, what the hell happens to this angle? What's its angular velocity at this point? And then, and if it has a positive angular velocity, it would be rotating this way. But if it's closing this angle that it already has, then it will have a negative angular velocity. So we're gonna, so that's one. We know that the angular velocity of this is, so I'm just gonna say you can do theta 2 dot or omega 2. That's gonna be a negative number. Now when it comes to acceleration, I'm not gonna tackle that animal, because maybe that's why we set this up. All right, well, let's get some intuition on that acceleration, because doing this is going to give us a few different points, and you're going to be able to get the change in angular velocity, fairly easily. But we're going to get two different angles here. Oh, and well, the way I did it, I didn't get enough. We need, we need three separate angles. The angle 30, an angle before, and then an angle later. And then once we get those kind of 3 points, then we can actually have two angular velocities. guesses for that, and then we can figure out the change in angular velocity. But there might not be a whole lot of difference between those angles, so it might be, finding the angular acceleration with this kind of the 3-point method is still, iffy to actually get some. But we'll see how we do. All right, so I just kind of know how these things work, but still, my intuition could be wrong. If I bring this up to a totally horizontal, and so from this bar right here, let's say I just move it just a little bit. Doesn't this like have to move a whole lot? You know what I mean? Because it can't just move down this line. It has to move in this direction. So if this is totally horizontal, just a small movement here makes a big movement here. Okay, and hell yeah. Now, so I could understand that, and then I was just thinking, well, once you get to about, well, now let's do it, yeah, I don't know, you know what I mean? Like, and then if I move this, is that going to be less of a movement? That's where, I don't know, my intuition isn't 100%. I'm actually going to stop the camera to see if I can gain more knowledge. Alright, hell yeah. And this problem doesn't ask what the velocity of this point is in the acceleration, but you could easily solve for that, and I do. I just haven't made that video yet. But that's where my mind was going, was the velocity of this. All they want to know is this angle. So if this is a horizontal, that angle's 90. And I don't know, does that angle change drastically? It seems like it does. So it seems like the acceleration of this angle is going to be in the positive direction. Oh, well, hold on. You can't just say that it stopped. That I was confusing. I was confusing like, oh, this thing stopped and then starting to move. No, it's moving at a constant angular speed. So the velocity of this angle is Alright, sorry about that. My camera juiced out. Okay, so I think I have something in mind here. As this thing is at a horizontal, this angle is collapsing fast, and that's its angular velocity. This thing is moving, like the change in this angle. See, I'm confusing the change in this angle with acceleration. No, the change in the angle is just called angular velocity, and that's going to be a large number because from here to here, hey, that change, let's say it took 1 second to go from here to here, hey, that's a big change in angle. Maybe like 15, almost 45 degrees, 90 to 45. So just keep that in mind. Now we're going to bring this all the way to the extreme and bring this lever arm down here. Maybe just back it off a little ways. But again, the angle that we're measuring, oops, sorry about that. The angle that we'll be measuring is the angle of this member, AB, that it makes with the horizontal. So you can see right here the angle is almost 0. If we bring it to totally vertical, it is 0. And so what we can see is that with a large change in this angle over here, we hardly move. This angle hardly changes. It's still reducing. You're still going from like 5 degrees to 0 degrees. But look at this. We swept off the same amount. I'm going to sweep from here to here, and this angle just changed by 5 degrees. Now let's sweep off that same amount. Once it's horizontal, we're going to move that same distance, and whoa, this angle swept from 90 to 45. Okay, so that's probably going to be the major aha moment of this problem. And even setting it up, we'll get to this little paper thing, isn't going to totally explain exactly what I did. It's not going to take it to the extremes. It's going to set up the problem as is at the 30 and measure a couple angles forward and back, and then it's going to give you those numbers. But now what we know is that this angular velocity, hell yeah, is going to be pretty decent. It's going to be a negative number, and then also it's going to be from, let's just spell it out, at time is equal to 0, this angular velocity of 2, or theta 2 dot, is, I don't know if you say it theta dot, but I think you do. Anyway, so that angular, and this is going to be in radians per second, maybe, let's say it did take, well, let's say it took 1/10 of a second to go from here to here, because I think that's about what this problem is. That's the other thing to get used to. This will be good. So this thing is rotating at 0.8 radians per second. I always joke around that no one knows what the hell a radian is. You know, that's where you have to kind of draw a circle and be like, okay, here's the radius. I measure out that with a string. I drape it up the circle. I get to about there. Hell yeah, that angle sweep is 1 radian. And there's going to be 6 of them. And then you're like, oh yeah, no duh, there's 2 pi, which is 6.28, but just remember 6. Hell yeah. And so I'm going to sweep out 60 degrees, 1 radian, in a second. This is 0.8. So basically this is 60 degrees right here. So in 1 second, I'm going to go from there to there. So now you have like a visual of how fast this thing is spinning, which is really important. 0, 1. So it's not moving super fast, but hey, this actuator might go a little faster. That's what we're trying to find. We're not trying to find the velocity of this point in this video. We're just trying to find the change in this angle, its angular speed, you know what I mean? That's the change in angle per time, and then we're going to figure out the change in that, the angular acceleration. And we're basically there. So we're even going to get some numbers on this. So I think in about 1/10 of a second, so this thing is going to change by 45 degrees. Well, again, hey, if this is 90, if this is 1 radian, 30 degrees is 0.5 radians. Okay, so what's 45? Well, that's kind of halfway in between. It's 0.75 radians. So if you know nothing about radians, at least spell out what 60 is, what 30 is, 0.5, and then for sure kind of what 45. And then look up the correct answers. This one's like 0.78. This one's 0.5, what is it, 23 or 32? Who cares? I think it's 0.523. But yeah, who cares? 0.5, 0.75, and then at 60, that's 1. Even though it's like 57 degrees, not 60. All right, but booyah. So what do we have? We're going to say in 1/10 of a... So our radian change went from 1 to 0.75. So we're going to have... And omega 2 is, by definition, change in the angle of this angle 2 divided by the change in time. So we're going to have we're going to go from 1 to 0.75. So we're going to have a change of 0.25 radians. Now, if you know 30 degrees is no, that's not even true. Hell no. We're going to go from 90. We're going to go from 90 to 45. So 90 actually will be 1 radian plus 30, so that's going to be 1.5. So 90 degrees is 1.5 radian. And we're going to go to 0.75. Okay, hell yeah. Glad I didn't mess that up. We're going to go from an angle of 90 to 45 in just 1/10 of a second. I feel like that, you know what I mean? That's a pretty good approximation for a problem. And that's more than any... That's more than any person would actually do on this to be like, oh, kind of getting a feel for it. So I feel like we got some gold here. So the change in angle is going to be 0.75 radians. Again, that's 45 degrees. It's going to go from an angle of 90 to 45. And we're just going to say about 1/10 of a second. So hell yeah. Divide by a 0.1. This becomes 7.5 radians per second. So I'm going to think... that might be the angular speed, and it's reducing, so I'm just going to say that's negative. Now I think this is actually way the hell off, because we're just trying to find the angular speed right at this point, you know what I mean? Because from here, let's say we go another 1/10 of a second, well, this looked like it went from like 45 degrees to like, what's that? Like 40 degrees, you know what I mean? So let's try that out. So let's say it only went 5 degrees. So if 0.5 radians is 30 degrees, we do 0.5 divided by 30 and then multiplied by 5. Hell yeah, that's going to give us 0.5 divided by 30 times 5. So we're going to have a change in 0.083 radians per 0.1 seconds. And this is going to give us 0.83 radians per second. That would be, and that's going to be reduced. So I don't know, somewhere in between. So we're a factor of 10, just awfulness. But at least we're like going down the right paths. You know what I mean? Because yes, the average angular speed from horizontal to this position, if we say that swept out 0.1 in 0.1 second, you know, it was probably like 0.2 seconds for this, so this probably gets reduced. Anyway, all right, hell yeah. All right, so let's see if that initial guess kind of pans out in what we learn from this. So we have this arm at 80. We're going to have this at 60. And the only cool, I mean, one of the cool things that I did with this is I actually took a hole punch. So then I could kind of figure out where this initial line was. So I got that lined up. I already poked a hole that I could kind of see through. Again, I hole punched again so I can really line that up. And then so once I did, I just hit that mark right there. All right, sweet. And let's, yeah, that was going to be the initial point. And then so I'm just like, well, hey, let's just sweep it. So let me line it up again. And then let's see if I can find this other point. So then I just swept it down. I actually wanted this to come right to the bottom right here. And then booyah. Then I just made another point right there. Okay, so but that's just going to be 2 angles. But yeah, let's work with that. The only thing on this one, which was a bummer, is I would almost need these to be like see-through, because let's take out this pin, and I should be using, you know, not a pen. But okay, so here's going to be the first angle. I'm just going to make all the angles real big so we do have a protractor. Hell yeah! And then this goes. Oh, this wasn't time 1. I don't think. Oh, holy hell! I'm just doing everything wrong. My bad. So this was supposed to be. Or where did we mess up, man? That sucks. Okay, so this was the 80. I just got to make sure we didn't totally hose this. So we had a pin there. Right here is the initial. That's going to be that halfway point. And then we got to there. Okay, so my bad. I just hosed this line. You know what I mean? This is the origin point. And then so we're going to draw this line right there. So we can get our initial angle, and we do have a protractor. So I'm just going to get this right there. And hell yeah. So this says we are at, you know, it's just flipped upside down. But yeah, we're at, oh, that's a bummer. They're taking all the, that's weird. Oh, this is not a protractor used by engineers, because engineers always start with the angle over here as 0. But maybe you, yeah, that's, and even in here, oh, that is, no, is it, did I just mess up? Oh, no, never mind. Well, the angle is 60. This problem is unique because they're taking their angles from the vertical. So they're saying this angle is 30. Cool. But we don't even actually care about that angle. We just want to care about this one. So let's get our paper back in here. And we're going to go from there to there. Okay, hell yeah. And we do have this vertical. So we're going to get kind of right in there. And hell yeah. So this angle right here says 40. It's like 41.8. That's pretty decent. So we got 41.8. Okay, so now we swept it to a new angle. So, you know, now we're here. I don't even need to draw this one in. But we swept it down to here. Now we got a lot of lines going on. But here's like time 2, here's time 1, and then here's time 1, and then here's time 2. And so now this angle from the vertical, so we're just going to kind of come, we just have to make sure that we kind of know where that angle is on the graph paper. That is why graph paper is good, because we can just kind of come right in here, mark that with right there, and you know, hopefully we're close enough. So now we're at an angle of 20, I would say 21.8. Cool. Is that right? That seems like a... So yeah, this angle went from 41 to... yeah, and let's draw this line in. Yeah, so this angle now is 21.8. Okay, booyah. And I said we didn't need to measure this. Hell yeah, we do. So this angle right here is going to be 30 degrees. And so for this second angle, we need to measure what it was. And so we're going to come right in here. All right, booyah. And this says it's, oh, this is difficult. All right, so we're 45.8. Cool. So this is going to be 45.8. Okay, so now from what our problem says is that we have an angular speed of 0.8 radians per second. Let's change this to degrees per second so we can kind of get a feel for it. We're going to say there's 2 pi radians in a 360 degree circle. Hell yeah. Radians cancel and we got degrees per second. So we're going to do 0.8 times 360 divided by pi. Whoa. I get so used to just doing 0.8 times 180 divided by pi. So this is going to be 45.8 366 radians per second. I'm going to store that in my calculator. We'll do alpha r just because I'm using other letters at the moment. But again, 0.8 times 360 divided by 2 pi. All right, so hell yeah. So this is how much is changing. It's going to change 45 degrees per second. We had a change of 45.8 minus 30, so we had a change of 15.8 degrees. So let's use this as our ratio. We're going to divide by 45.8336, and you'll see, and I'm sorry I put radians there. This is degrees per second. So we're going to have degrees per second. Degrees cancel, and then seconds pops upstairs. So we're going to have that divided by alpha r. And the time frame on that, so it's going to be a time frame of 0.3447 seconds. Cool. So now we know how much this angle changed. This angle changed by 20 degrees. So we're going to have 20 degrees in 0.344 seconds. So let's do that. 20. I'm going to store this value, though, as my alpha t. And we're going to do 20 divided by alpha t. And that's going to be 58.02 degrees per second. Let's change this to radians per second. So we're going to do, I'm just going to do 180 degrees for a half a circle is pi radians. All right, hell yeah. Degrees cancel, and we're going to get radians per second. Once we divide this by 180 and then multiply by pi. So we're going to have 1.012 it's not that accurate, but 1.01 radians per second. And since, we probably have 1 degree of accuracy. So great, it's 1 radian per second. Maybe it's 1.0. Maybe we can say, hey, we're pretty close to 1.0. Closer to 1.0 than 0.5 or 0.6 or 0.4 or 1.4 or 1.5. You know what I mean? So there you go. So hell yeah. And I should have done this. So I didn't get the negative sign in because the second angle on this one is 21. So we go 21.8 minus 41.8. So we have this angle is reducing itself. So it's going to be negative 1.0 radians per second. All right, hell yeah. Okay, so with the 3-point method, you just have to sweep out the same amount of time. So we went forward with this. We just need to sweep out the same amount of time this way. So here, and the angular speed is going to be constant. So we went from 30 to 45.8, so we're going to go 45.8 minus 30, and that's 15.8 degrees. So we're going to do 30 minus that, and what we need to do is mark out a 14.2 angle. So let's do that right now. So we're going to come in here, and we're going to mark out 14.2. So we got 15, 14.2, booyah. And, oof, I don't think I can do that left-handed. Alright, so here's going to be our angle, our initial angle. Well, if we started, so the problem did have a 30-degree angle, but if we turn time backwards, we're going to be to there. And so, hell yeah. So we're going to, and this is cool. I got these thumbtacks, so let's use them. I'm just going to pop this one through the paper, and at least, it kind of frees up a hand. What I wanted to do is just like, hey, what's the simplest thing that I could do where I wouldn't mind repeating this, where I can just get on with life and go do it. Okay, so we're going to be on this, we're going to be somewhere on that angle. Sorry, I have to get my head in here. Okay, booyah. So there you go. So that's going to be right there, and then I'm going to come in with this thing right there. Perfect. So we swept back the same amount of time, you know what I mean, whatever that alpha t was, 0.3 seconds basically. And then this thing is still tracing out, the cool part about this problem is it's tracing out this vertical line always. And so this is our vertical line right here. So booyah, it's almost horizontal. This is pretty cool. Whoa. Yeah, it really is. So this is going to be hard for me to see. And I wish I had this thing just a little bit more. I should get my hole punch down here. So hell yeah, let's do that. All right, hell yeah. So we're back and we have this hole punch. So this will come in real handy. And don't have to get too fancy. Oh man, I'm freaking out. Alright, hell yeah. Okay, so, yeah, I don't even know if it's going to reach. But we'll find out. Oh, I think this point got off. Yeah, so let's hole punch the hell out of this, too. And, whoa. I don't want to ruin. Oof, almost ruined it. But hell yeah, so we're going to be right in there. And, yeah, I think that's fairly close. And, okay, so we're sweeping that out perfect. So we're sweeping that out to, I would say right there is pretty decent. And, booyah. So we have that point marked, and we have that point. Okay, we're done. And so I'm just going to mark this. Let's get this pin out of here. And so, alright. Oh, is the angle... Wait. No, so here, our point was up there, right? Yeah, so here is that angle. So here's angle 2 that we're trying to find. Oh man, I hope I went through it decent. Cool. So now we want to find this angle from the horizontal. And so, yeah, perfect. It's just right on this line and right on that line. Alright, and then where is it? Just right there. And I want to be as accurate as possible, but also just kind of, okay, who cares? Okay, so how did we measure? So that second angle gets measured from this horizontal this way. So we're sweeping out from here all the way up there. And yeah, we're at 80, 81, 82. I think 82 just right on the nose. So I'm going to say, hey, this angle is 82 degrees. So now you can see, yeah, that's fascinating, because like that's not going to be very representative, because you see how much angle swept. There's little here and then there's a lot there. But just a little foreshadow, this was low. Doing the problem using differentiation, we're not going to go over that in this video because it's just, look at that. It looks like something you put on a cave. But anyway, so the actual answer is negative 1.24. And so right off the bat, going this direction, we're getting 1.2. But that's going to be more, like going this direction is going to be more representative of the angular speed compared to going back the other way. Because we already said that. You go from horizontal to here, in that same amount of time, you're just covering hella distance. And so, alright, sweet. So let's do that. So we're going to cover 82. Well, it's this minus that. So 41.8 minus 82. So we're actually reducing this angle. It's big and wide open at 82. We're reducing this angle to 41.8. And then we're dividing by alpha t. And we're doing that in that amount of time. So this is the change. We're going to have negative 116.6 degrees per second. That's going to be the angular speed of that arm. Divide by 180 times pi. And we get negative 2 radians per second. So now we can take the average of both of these and say that, and I got to store this as maybe alpha q. Sweet. So we can do alpha r plus alpha q. We can add them and then divide by 2. My alpha r isn't negative, so negative alpha r stored as alpha r. So, so going forward, oh, bummer. And, oh, and then alpha r, I need to divide by 180 and then multiply by pi. No. Damn it. Wait, where did we store this value at? I totally forgot. So alpha, oh, alpha r, whoa. Negative alpha r stored as alpha r. Maybe I'll keep that. What the hell? So we had 15.8 degrees divided by alpha r. Oh, which was our angular speed in degrees per second. Okay, I can dig. I'm going to store alpha r as alpha u. My angular speeds are usually omega, w, and then v, and then u. So those three are reserved for angular speed. Okay, sweet. So we got 15.8 divided by alpha u. That's going to give us that time. Okay. Yep, I can dig. And then we had a... Oh, I see. Yeah, that 15 degrees was the constant speed here. This moved 15 degrees, and then we moved it actually back 15 degrees. Okay, so none of that really applies, but it does give us our change in time, and we already have that. So moving on, I just don't know where I have this first one. So we have negative 20 divided by alpha t, and then divided by 180, multiplied by pi. So this is going to be the angular speed. I'm going to store it as alpha r. This alpha, so now we'll do this one. 41.8 minus 82 divided by alpha t. And again, we're changing the angle. The angle is changing by 40 degrees in this alpha t seconds, in that 0.3 seconds. So this is going to be, we're going to reduce our angle by 116 degrees per second. We're just not traveling a second. We're just going a third of a second. But this is our angular speed. It's just in degrees per second. We need to divide by 180, multiply by pi, and then so that's our angular speed. So we have alpha r and then alpha q. Here's our angular speed coming in. Here's our angular speed exiting if we took that that amount of time. Okay, so we're going to average those just by adding them. R plus q divided by 2. And cool, so we get an angular speed of negative 1.5 radians per second. You know what I mean? So there you go. So this first one was more representative. And if you could see that, you know what I mean, you could be like, well, there's a lot of different averaging ways. But, I mean, typically you don't want too big of a sweep. So I would actually, and we already knew that was going to happen. If this got up to vertical in just a short amount of time, it was going to sweep about, 40, 45 degrees. So that's what we see, but that's not representative of the speed right here. The representative speed right here is closer to 1 radian per second. But if you go back and then forth across that 30, if you went from 31 degrees and then 30 or 29 degrees and then 31 degrees, that change in angle before and the change in angle after would be a better representation of the actual angular speed of this. Okay, hell yeah. I was just noticing that we could average this with 1, you know, so I'm going to actually store this as alpha p though. So alpha r plus alpha p divided by 2. Whoa. Alpha r, alpha p. Yeah, so if you had alpha r plus alpha p divided by 2, you would have, that would get you the answer pretty much 100%. But the whole idea is, like, you haven't done this. This is your first step. So you're just trying to get, like, in the ballpark. The fact that we got negative and 1 is super useful. We don't know if this number is 0.001 or 1001. You know what I mean? So that's the whole idea of setting up a problem like this. Now, let's see if we can figure out the change. Because we have alpha r and then alpha q. This is going to be the angular speed in radians per second approaching. So alpha q. And then alpha r is angular speed exiting. So if we take the second minus the first, alpha r minus alpha q, divided by alpha t, hell yeah, that's going to be the angular acceleration. And this says our angular acceleration is going to be a positive 2.97 radians per second squared. And if we go to what the actual answer is, well, it's 1.94. But again, you know what I mean? Doing it on paper like this just gets you into the ballpark. I'm kind of disappointed it doesn't get you, like, super correct. But look at this. We have a tiny sheet of paper. You know, I mean, we're just kind of doing things. If I wanted to take this to the ping pong table, we could blow it up huge and actually try to hone this in. Alright, but that's it for this video. So what we did is we took a problem, you know, we kind of did some things with it, took it to the extremes, tried to figure out at least positive and negative, like, hey, is this thing collapsing? Yes, this angle's collapsing. It's going to be a negative angular speed this way, because we're saying, we've already defined this. If this angle is positive this way, and this thing's spinning this way, that's going to be a negative angular speed, negative radians per second. And we see that that's going to be real fast. It's going to be negative real fast, but then as you go, it's going to slow down, and it's not going to be as much. So the acceleration is actually going to be in the opposite direction. It's just kind of confusing. We're saying this is the negative direction for angle, and we're saying this is the positive direction. So if we're having yeah, this is the good thing to end on, because this happens all the time. You have a very fast negative speed, but we're actually reducing that negative speed. And so our acceleration is in the positive direction. Doesn't mean that this thing is spinning in the positive direction. It just means that it's slowing down. You're going hella fast towards the ground, and then, hey, let's accelerate you up above the ground to actually cushion your fall or something like that. So that would be a positive acceleration, even though your speed is negative and hella negative. Alright, so thanks for joining me on this one, and guess what? That's a video.